Hey everyone, and welcome to this explainer. I'm absolutely thrilled to have you all here today. If you're the kind of person who geeks out over how massive, mind-bogglingly complex systems are built and managed, well, you are definitely in for a treat. Today we're looking at a monumental, literal game-changer of a shift happening right now in European infrastructure planning. We're talking about moving from a world of totally closed systems into a brand new era of open-source modeling. And the implications for data engineers, developers, and energy planners, they are absolutely massive.
Right off the bat, I want you to just stop and think about this question for a second. How do you actually plan an entire continent's power grid for the next decade? The stakes here literally couldn't be higher. We're talking about billions, with a B, of euros in investments, transitioning to renewable energy, making sure the lights actually stay on across dozens of different countries, and integrating completely new tech like green hydrogen. It's like a giant puzzle combining energy system planning, heavy-duty data engineering, and macro infrastructure modeling.
Okay, let's dive into this. Here is our roadmap for today. We'll start with the grid planning bottleneck, introduce Open-TYNDP, look under the hood at the architecture and workflow, explore modeling topologies, break down who actually benefits, and finally, chart the road to 2026.
Section 1. The grid planning bottleneck.
To really get why this innovation is such a massive deal, we kind of have to look at what was holding us back. Traditionally, grid planning relied heavily on legacy systems. We're talking proprietary software, manual data assembly, serious vendor lock-in, and these black box graphical user interfaces. If you wanted to validate another institution's results, it was incredibly difficult. It's literally the equivalent of trying to audit a skyscraper's blueprints, but they refuse to show you the math. But with Open-TYNDP, we are moving from static spreadsheets to a real code-to-concrete approach. We're looking at open data structures, automated scripts, version-controlled pipelines, and true collaborative auditing. It's just a complete 180-degree turn in how we handle infrastructure data.
And I really want to highlight this powerful quote from the source material. Reproducibility is now a primary requirement, not an afterthought. For all the developers and data engineers tuning in, this right here is your core takeaway. The era of non-auditable grid modeling is done. It's coming to an end. We are moving into a space where every single calculation, every assumption, and every output must be completely deterministic and reproducible. No exceptions.
Section 2. Introducing Open-TYNDP. So, what exactly is the whole shebang? Well, Open-TYNDP is an open-source toolchain and model dataset. It's built collaboratively by Open Energy Transition, or OET, and ENTSO-E, which is the European network of transmission system operators for electricity. Their end goal? To replicate and eventually completely replace the legacy workflows used for the 10-year network development plan. And actually, what's really fascinating from an architecture standpoint is that this is built on a soft fork strategy extending from PyPSA-Ur. That's a highly respected open-source Python framework for power systems. So they're taking years of rigorous academic research and injecting it straight into official grid planning.
So the crucial point here is the core philosophy driving this entire code base. They are aiming for full transparency of the math and the code and absolute reproducibility of the results. One of the most interesting design choices, honestly, is that they store no intermediary results whatsoever. Everything is computed deterministically right from the raw data and explicit config files using a fully automated snake-make workflow. This setup allows for independent community benchmarking, which ensures that the model remains bulletproof and trustworthy.
Section 3. Architecture and developer workflow.
Just to show you how real this is, as of the latest source data, the project is actively iterating and currently sits on release version 0.7.1, which is hosted over on Zenodo. This isn't just some theoretical white paper code, it's a living, breathing repository using robust CI/CD testing frameworks via GitHub Actions. In fact, this specific release was pushed to squash some bugs, specifically temporary pins to handle constraints in their optimization models like generator limits that were spitting out negative objective function values. So yeah, this is real, active software engineering applied directly to macro infrastructure.
Now, if you actually want to run this yourself, the workflow is brilliantly automated. Step 1, you can install it natively on Windows using a Pixie-based executable, which just handles all the environment setup for you. And if that fails, no worries, they have full Conda fallback environments ready to go. Step 2, verify your pinned Python and package requirements. Step 3, review the explicit YAML config files to map your input datasets. And Step 4, you just execute the snake-make pipeline. Compare that to the old days of blindly clicking through proprietary black box apps. This script-driven approach is just a massive, massive leap forward for accessibility. Section 4. Modeling topologies. Now, what's really interesting about this slide is just the sheer immense scope of the data being ingested here. This isn't just a simple electrical map on a screen. These integrated models include the standard electricity reference grid, sure, but they also include the hydrogen reference grid, complete with import potentials. It models offshore wind hubs with offshore electrolyzers. It even integrates incredibly complex datasets like PECD version 3.1 for highly detailed climate and renewable profiles, and PEMMDB version 2.5 for hydro inflows and capacities. They aren't just making a map, they are building a complete sector-coupled digital twin of the entire European energy landscape. Right, so once you actually have that digital twin, you need a way to evaluate new projects, right? That's where the cost-benefit analysis, or CBA, comes in. Open-TYNDP features this really cool automated framework that runs TOT, take one out at a time, and PINT, put in at a time methodologies. Essentially, you take a proposed transmission line or maybe a massive battery storage project, you drop it into the model or take it out, and you let the optimizer run. The software then calculates complex socioeconomic welfare indicators, CO2 variations, and even non-CO2 emission impacts. It's a rigorously mathematical way to answer the ultimate question, is this billion-dollar project actually worth building?
Section 5. Who actually benefits?
And this brilliantly illustrates exactly how this open ecosystem ripples outwards. For transmission system operator planners, they get way faster iteration and the ability to easily run sensitivity analyses. For ENSO-E leadership, having this open to independent community benchmarking just builds massive legitimacy for their long-term plans. For researchers, wow, they finally have full access to a pan-European model calibrated to the official 2024 TYNDP data. And perhaps the coolest part, for global planners completely outside of Europe, this provides a highly reusable, open-source framework that they can just adapt for their own regional energy planning. It's pretty amazing.
Section 6. The Road to 2026.
Now, it's pretty important to manage expectations about what this toolchain actually does and what it doesn't do. The scope is very deliberate. They want to replicate the existing closed models, validate them openly, and then expand. So currently, it is strictly designed to model long-term capacity, scenario analysis, and infrastructure investment. Actually, scratch that. It's more accurate to say it is explicitly not designed to solve real-time, second-by-second grid dispatch or short-term market simulations. It's a long-term planning tool.
Let's move to WADA and see how this builds a really smart, phased risk mitigation strategy leading up to 2026. In 2024, the major priority was to successfully replicate key figures from the 2024 TYNDP national trend scenario. Moving into 2025, the laser focus is on allowing the community to thoroughly audit the mathematical and computational foundations. This is what builds the trust required so that by 2026, they can fully align the open codebase to run the actual 2026 TYNDP cycle. It's a brilliant stepped approach to overhauling continent-level planning without breaking things along the way.
So we've just seen how Europe is actively moving to this fully open, reproducible, code-driven model for its future power grid. I want to leave you with this final, provocative thought. How might open-source infrastructure modeling transform your own local grid planning? Seriously, whether you're dealing with a national grid, a microgrid, or regional infrastructure, the core principles of transparency and automated reproducibility that we've explored today, well, they're the future, for sure. Thank you so much for joining me on this explainer, and keep learning.